presentation, I want to give an overview of IBM Watson, the software that won an exhibition match against Ken Jennings and Brad Rutter, two of the most recognizable winners on Jeopardy. And in that context, I would like to argue that IBM Watson should properly consider to be an engineering marvel. We know of other engineering marvels, mostly in civil engineering. Think about the Sears Tower or the Brooklyn Bridge or the Golden Gate Bridge. We look at these things and we think, wow, they are pretty. Plus, I mean, they're really well engineered. They held up, they stood the test of time. So I want to start out with this figure over here, and eventually we'll sort of fill in some of the details. So this was from an article that was written by many of the key people on the team. So the team leader was Dave Ferrucci, but David Gondek and a bunch of others also played major roles in this thing. This was clearly a team effort. Hopefully you saw the videos about the exhibition match, as well as that sort of showed you images of some of the people who developed the software. So let's have a look at this diagram over here. So in Jeopardy, we have a question and we want to have an answer, but we also want to have a confidence with the answer. So we don't want to buzz in if we're not very confident in the answer. What's unique about Watson is it's a pipeline. It's a one-shot traversal of the pipeline. Most AI systems sort of have a loop. They go around and around and around, get better and better and better, but they only had a one-shot deal over here. What was truly amazing about Watson, and that's where the engineering marvel comes in partially, is the way they did this. So you kind of have to imagine that there are really two phases over here. This phase on the left and the phase on the right. So let's figure that out. They start with a question, and of course the first thing you need to do is to figure out what's the question all about. And again, we'll say more about that. Then, based on the question, they sort of try to find answers. So they have hypothesis generation. They have what they call a primary search. They look at things like document search. They even looked at TOD as a title of document. They looked at passage search. Some of these things are simply keyword searches. Some of them are the same sort of stuff that Google does with, sort of using indexes very smartly. Then they sort of had the same thing as Google does, so their own internal search engines. They have a stash of pre-processed data. And so they sort of try to find the answer to the question. They do some small filtering over here to get rid of the most obvious garbage. And here's a strike of genius. So suppose the question was, did Einstein win the Nobel Prize? And so suppose you cobble something together, you say, I think he might have won the Nobel Prize. What they do then is they turn the question into an answer. So rather than sort of going on with, hey, did this dude win the Nobel Prize, they actually put his name in it. So they say they're then looking for documents that have the following sentence in it. Einstein won the Nobel Prize. And as you might imagine, there are many, many more documents that have that statement in it rather than a question and a corresponding answer. So what they do over here is they again look for, they have their sources and they search through them to see whether that sentence appears. Now, as we will see later, sometimes there are similar answers, and so they synthesize those in the final merging and ranking to sort of say, yeah, all of these are really the same answer, and so that will obviously increase the confidence. And so that's what they have over here. Now, let me say something about another aspect of engineering marvel. So you might think that IBM sort of simply plugged Watson into the internet, and so let it search things live. Well, they didn't do that. They had to produce an answer in 3 seconds, and that's really hard to do with searching the internet. So everything they did, they kind of pre-processed or downloaded things from the internet. But they didn't just download everything from the internet. As you know well, a lot of the stuff on the internet is garbage. I mean, think about blog entries. Oh, they're horrible, right? Here are just blurting things out without much background and knowledge about stuff. No, they only downloaded the good stuff. So they downloaded Wikipedia articles because, well, they are very highly curated. I mean, people review them, and the reviews are being voted on, and eventually articles go live or they have a disclaimer on them. Similarly, newspaper articles, right? New York Times, I mean, very highly vetted information, dictionaries, Cambridge, Oxford dictionaries, Encyclopedia Britannica. So they only took the good stuff because they kind of knew that, the good stuff, the information is reliable, right? That's what it's all about. But again, they had many different sources just because there's strength in numbers, right? So that's kind of like another aspect of why Watson was an engineering marvel. So let's have a look at some images that I obtained from taking a course on Watson several years ago. This was actually put on by IBM Watson. So what's a challenge with IBM Watson, and something that people really didn't do well before, is that they have what they call open domain question answering. As you know from watching Jeopardy, you don't know ahead of time the domains, and they're typically, well, there are several domains for which they ask questions. So this is open domain. This is not, oh, you know what we're going to be asking you about. Maybe an exam situation is going to be about these and these topics. No, it's really open domain. The other thing is, so it's a broad domain of knowledge. The other thing is that the questions are posed in natural language. Again, this was almost 10 years ago, right? Or they certainly developed it 10 years ago and before. We sort of like had queries, database queries, right? And so now we have to add natural language. And natural language, as we will see, well, as we have seen already a little bit, is highly ambiguous. So we want to have a precise answer. If you ever watch Jeopardy, ever so often Alex Trebek or the jury will sort of like ask for clarification for an answer that they think, yeah, the person got it right, but they just didn't phrase it properly. Again, it's very important that the system knows, that its answer is most likely correct. So we don't just want to blurt things out. And sometimes, again, they ask on Jeopardy for clarifications. They ask for justifications, not necessarily justifications, but they ask for clarifications. And again, all this had to be done in less than 3 seconds. Otherwise, other people will buzz in. So let's contrast that to using a search engine. So suppose you have a question, right? If you so a lot of times with Google and like search engines, you kind of need to know, okay, let me sort of come up with a couple of keywords. And so you use the search engine, they find documents containing the keywords, they deliver them a ranked list, and so you skim the documents, you read them, you find your answer, and then eventually you sort of say, yeah, I think I know the answer. But with what they call expert QA, is we ask the question in natural language. And so what the system has to do is, obviously has to understand the question in one way or other, or has to parse it properly, produce possible answers and evidences for the answers, analyze it, and deliver a response. And so we deliver a response, right? Yes, Einstein did win the Nobel Prize, something like that. Now, a key technology that they used was UEMA. UEMA is now, it's an Apache project. It's available open source. And as a matter of fact, we're using it for the human-robot collaboration project that I'm working on, the human-robot collaboration project. So it already existed before IBM Watson, so I took a hold of it, but it wasn't really great software. It was brittle. And so they took it and they streamlined it and made it robust and reliable. That was a key thing. So part of what we do in good science and good engineering, we build good tools, and this was one of them. And so this is an example of the UEMA pipeline, and we'll see about this thing. We'll see more about this thing later in the term. So what we do is when we have a document, we initialize a CAS. We read the document and we sort of like say, okay, well, we'll just put a string over here. So these are structured objects. Then what we do, and these are called annotators. So the annotator will process something and produce these CAS objects. Then we'll pass it on to the next one over here. They pass a sentence. So this is a parser. and they add a parse tree to this CAS object. Then it gets passed to another annotator, say named entity recognition, and they may identify, we're talking about a person over here, about a date over here, and that information also is added to the CAS object. And then we do other things. So that's how this thing works. This is how this UEMA pipeline that we've seen earlier works. We have these CAS objects. They eventually will look at CAS multipliers that process information. One of the key things that they had to figure out is they call this LAT detection, which is lexical answer type. So as you may know by watching Jeopardy, they never really come out asking a question directly, right? They always have these clues. So here's one, a new play based on this, Sir Arthur Conan Doyle Canine Classic, opened on the London stage in 2007. So the hard part of Jeopardy is like trying to figure out what are they asking in the first place, right? And so clearly they're asking about this, right? Some sort of classic that appears to be a play. So what they need to do is they need to look for noun phrase with determiners, this or these. Here's another this. Sometimes it's pronouns and other things. So the LAT detection, lexical answer detection, simply tries to figure out what are they asking. Are they asking for a person? Are they asking for a play? So it's a little bit of named entity detection, right? Are they asking for a female person? Are they asking for some sort of entity, right? And that was a key component of Watson. Another thing that they did is they analyzed the question classes on Watson, on Jeopardy, I'm sorry. And you can Google this thing, but there's a record online of all the questions ever asked on Jeopardy. And so, smart as the engineers were, they downloaded that thing and looked at it, and they studied it. So, look at this. They even have the frequency. So, 14.2% of the questions on Jeopardy are about definitions. 7.2% about category relations. They're puzzles, dates, multiple choice, lots of things, right? And so this is useful information. Like if you're not sure that your question processing, led to that, I think they're asking for a definition, but they may also ask for like a puzzle. Well, if you're unsure, maybe you want to bias it towards this one over here because they just appear more often. As I mentioned, they have these CAS multipliers. What they do is whenever a task needs more CPU cycles, they multiply those things. Actually, they have another diagram here in just a moment. This one here shows you the information flow from these CAS multipliers that we'll see in a moment. So the primary search will produce many, many results, and those results go into the final merging. So do the search results, the candidate answers, all this stuff will go into this huge, giant component for final merging. And by the way, this is they used logistic regression to do this thing. They trained a classifier, which is kind of mathematically speaking the same as a neural network classifier. So that's what they did. Nothing ever got thrown away. Well, some stuff got thrown away, all this garbage, but all the good stuff, so like the stuff that made the cut went to the final merging. Here is what I wanted to show that I mentioned a moment ago. They have these CAS multipliers. So the idea is based on the primary search. They go maybe to 100 databases. And then based on the candidate answer, they suddenly have 100 possible answers for each of these questions. And so then they look for thousands of pieces of evidence and hundreds and thousands of other data sources or items that they want to get confidence on. So just very, very lots of processes that had to be dealt with. And as you can imagine, as you know from watching the videos, they kind of built a supercomputer for this thing. All right, that's all I have for the overview. I'll say more about some of these things in some of the other presentations. I will see you then. Bye.